video tutorial is about sound, but it specifically focuses on how it is created and the speed of sound in different mediums. You can find information on this on your notes from quiz 1D sound. Before we get started, I do want to point out you need to know about the Doppler effect and what it means and how it's done, but this video has nothing else about the Doppler effect because there's already lots of good resources online, YouTube videos and stuff that do a much better job of the Doppler effect than I could do. It's really tough to show what's happening in air and in solids when sound waves pass through them. So in this tutorial, I'll basically be using a super slinky to demonstrate the same ideas as sound traveling in air, but it'll be, energy traveling through a slinky. For this demonstration, what I did was on the floor of the classroom, I taped down these blue pieces of tape across the floor, and I attached one end of the super slinky to a leg of a lab station. And you can see by doing this, there's a mark 1 meter, and every one of these blue tapes is at 1 meter, so we can get a distance measurement off of the floor during the videos. So basically what will happen is I'll be able to stretch the slinky across the floor like this and create waves by moving my hand in different ways, side to side and back and forth. It'll make the waves travel across the floor. This first wave is basically a low frequency wave, and you can see if I pause, I can pause the motion of the wave, and I'll be able to take a picture of that, and you'll be able to see using these lines, we'll get an idea of what the wavelength is of those waves. Now this one is a different video. It's more of a medium frequency wave. And if I can pause it right like that, and you get an idea, we can use the blue lines here to get an idea of what the wavelength is for those. So here's a picture where I sort of combine both waves. On the top was the medium frequency, and the bottom is, or the top is the low frequency and the bottom is the medium frequency. And you can see by looking at the marks, there's a peak there, or crest, trough, crest, and they're almost right on the blue lines. This is basically one wave in 1 meter, which would give you a wavelength of 1 meter per wave. It's actually a little more than, it looks like it's a little more than 1 meter per wave. And then down here we have a peak, or there's a crest, a trough, crest, trough, crest. So it looks like two full wavelengths, 2 waves in 1 meter, which is a wavelength of ½ a meter per wave. So you can see that this is a faster frequency. It's about twice as fast. This frequency is about twice as fast as the frequency of the other wave. And we can compare these pictures because both of them are waves traveling through identical mediums. To see how a slinky is a good model for how sound travels through air, let's look at how sound's created. Basically, when you take something that can push, that when it vibrates back and forth like this and it pushes against the air, it will cause the air to push together and compress the air, which is really like high pressure area and high density because the molecules are pushed together. And then as the object pulls back the other way, it does the opposite. It pulls the air apart, and it's a low pressure area, almost like could be a vacuum, a low pressure, and this is low density. The molecules are really spread apart, so it's called rarefaction, like it's rare. The air molecules are found rarely in this area because it's like a vacuum. And you can see this, for example, a speaker. If you ever have a chance to kind of open up the front of your speaker and look at this, the speaker usually has a cone, and it's got magnets and wires that cause the cone to go out and in, out and in, out and in. And when it goes out, it causes this high pressure area, and when it pulls back in, it causes this rarefaction area, so compression and rarefaction. And then these waves travel across the air like this. The molecules vibrate right this way and travel across the air to your ear, for example, and then you can pick it up as sound. And sometimes we represent this type of wave with this type of wave down here. This is called a longitudinal wave because the waves compress and spread apart and compress and spread apart. But this transverse wave is the one we're pretty used to talking about in class. You can see as the graph goes up, that would be the peak or the crest, which is where it's high pressure, high density. Then it comes back down. It goes down the bottom to trough, which would be low pressure or rarefaction. That's the vacuum. And you can see how it goes up, again, crest, down, vacuum, trough, crest, trough, empty, crest, that's compression, trough, rarefaction, compression, rarefaction, compression, rarefaction. So sometimes we make sound waves, we draw them like this, even though we draw the shape of the sound waves like this, even though it's actually representing this high pressure, low pressure wave that travels out. So now we're talking about a tuning fork. You can kind of picture a tuning fork vibrating. This is like normal without the fork vibrating, and all the air is at its normal pressure. But as the tongs and the spread apart, it makes high pressure of the molecules, and then that high pressure wave travels through the air, and then the prongs go inwards as it vibrates, and that makes the rarefaction, or more the vacuum. And you get the idea what happens over time. So here's a tuning fork that's vibrating. It's high pressure, then low pressure, high pressure, low pressure, high pressure, low pressure, high pressure. And those waves travel across like this. And it looks like a straight line. And in actuality, it travels in all directions at once because you can hear the tuning fork all around it. But if you just look at a straight line from this one point, you can see the shape it makes. It kind of looks like a slinky. And I'll show you. So here's a video if you watch to see how a slinky really approximates the same thing as sound. When I move the slinky, instead of left and right, if I move my hand back and forth, you get something that looks more like a sound pressure wave. So it's like this. The hand goes back and forth, and you can see that the waves travel along the same direction that the slinky is stretched. And so that happens when you're moving back and forth like this. And you get high pressure, low pressure areas where the spring is compressed and pulled apart. So maybe you can see either one if I can pause it in the middle of, let's try that right there. There you go. You can see right here is where it's high pressure, where the waves, the slinky springs are pushed together, and then probably right about here is where it's the normal stretch, and right here they're really pulled apart. This would be like this will be compression and rarefaction, high pressure, low pressure, vacuum, if this was a sound wave traveling through air. So what I want to demonstrate to you now is how the speed of sound depends on the medium that it's traveling through. For sound, the medium could be air, water, solids, for example. In air, sound travels about 350 meters per second. Water, typically about 1,500 meters per second. And solids can be 3,000 meters per second or greater. So how are we going to do this with a slinky? I can't really change the medium of the slinky. I can't make the slinky out of water or out of solid, rock, and I can't make a slinky out of air, but what I can do is I can stretch the slinky different distances. And if you can tell by the blue lines on the ground, this one's 1, 2, 3 meters, and this one is stretched 1, 2, 3, 4, 5. It's actually stretched 6 meters, 6 meters long on the floor here, and it's 3 meters. And you can also tell by looking at the sort of the density of the spring. These wires are really close together compared to these right here. They're basically twice as close together on the top one as they are on the bottom one, because the bottom one spreads 6 meters across and this one's only spread 3 meters across. So here is Here's a slinky stretched 1, 2, 3 meters, and we're watching the waves move across. Let's get an idea of the wave speed here. And we're going to try to get it, let's try to time 2 meters. So as soon as it starts, I will hit the stopwatch and then stop it right there when it goes to ready end. So it was about 1.31 seconds. So let me try it one more time. 1.34 seconds to go from the beginning to 2 meters. 2 meters over 1.34 seconds equals 1.49, 1.5 meters per second. And that will be the speed of the wave when the slinky is stretched 3 meters. Now we can try it with this one where it's stretched 6 meters, and we can probably time 1, 2, 3 to here will be 4 meters if I go 1, 2, 3 to that line right there. So here we go. Let's try and nope, didn't do it right. Let's try again and go. Man, that's tough. 1.15 seconds. Alright, and this time it went 4 meters in 1.15 seconds. That gives me 3.47 or 3.5 meters per second. Okay, and here are the results. We can see when the spring is stretched 3 meters, it travels along at 1.5 meters per second, but when it's stretched for 6 meters, it travels along at about 3.5 meters per second. So stretching the spring makes it easier for the energy wave to travel from one end to the other, faster speed. So why is the speed faster when we stretch the spring out like this? Also, how does this relate to the speed of sound through different mediums? So what I like to do is use an analogy. Let's just say that you are hanging out with a few of your friends like this. You're in a line and all of your arms are outstretched and stiff like this. And the object was for you on this end to somehow signal the motion of the friend on the far end over here. And if your arms are all stiff and stretched like this, as soon as you push this on this friend right here, they're going to almost immediately push the next friend, next friend, next friend, and they're going to move at the end here very quickly. It'll only take a couple seconds to move this friend on this end. Now, let's assume that you guys are in the same line here, but your arms are kind of like wet noodles, right? They're just sort of hanging down, kind of loose like this. They're not stiff. And now you want to do the same thing. You want to signal the motion of your friend on this end. So as soon as you move, since the arm is loose, it takes a while for this signal this friend to move, and they move over, and then it takes a while to move down this way, move down this way. You can see it's going to take probably 4, 5, 6 seconds for the signal to go from here all the way down to this friend. So the speed of the wave across here will be slower than the speed of this wave right here. So it's the same thing for the slinky. If you imagine when up here when the slinky is fully stretched out like this, the spring is really stiff, like stiff arms, so the speed is fast. And down here, when it's not stretched out as much, it's loose. The spring is very loose, just like loose wet noodle arms, and so the speed is much slower. So let's take the analogy further and imagine that you tried another situation where you guys aren't even touching. You're just standing in a row like this. In order to move your friend here at the end, now what you're going to do is you're going to poke your friend right here. You walk over and poke them, and then as soon as this friend feels the poke, they're going to walk over and poke the next friend, and they're going to walk over and poke the next friend, and walk over and poke the next friend. Well, you can see what happens now. It's going to take even longer for this wave, this signal to travel, because you guys aren't even touching. So it takes longer for the signal to go because you're separated apart by some space. So that would be the stories if you use friends and how they're trying to send a signal across the room. Let's take the analogy even further. Assume that instead of a group of friends, you have a group of molecules. One way to look at when molecules are interacting with the chemical bonds are very similar to springs. You can picture the chemical bonds just like they're springs, and like in the top one, for example, in a solid, the springs are very stiff and solid, right? The molecules are attached very well together, just like your friend's stiff arms. And then in a liquid, they have the bonds, but they're really loose, like loose limp noodle wet arms or loose springs. And then finally, air, the air molecules, they're basically separated, and they have to almost essentially bump into one another to transfer energy from one to the other. So you can get an idea, if I have something that vibrates this molecule here in the solid, something vibrating like a tuning fork, and it would vibrate this molecule over here, it wouldn't take very long for an energy wave or the sound wave to travel all the way across like this. So it'll go very quickly. Over here though, in a liquid, if the tuning fork is underwater and it vibrates this molecule here, it would take a little bit longer for the signal to go across the liquid because it's like wet noodle arms. They don't pass the signal as quickly. And then, and finally in air, tuning fork in air, to vibrate these molecules, the molecules actually have to move across and hit the next one, and transfer the energy across. This takes the longest amount of time to go through the air. So now we can see why sound travels different speeds through different mediums. For example, in air, sound travels at 340, 350 meters per second because it's like you and your friends separated, and it takes a while for the signal to travel through the air. In a liquid such as water, speed of sound is something around 1500 meters per second, quite a bit faster because it's like you and your friends are holding hands, but with limp, wet noodle arms, and so the signal still takes a while to travel across here, but not as slow as in air. And finally, the speed of sound in solids can be pretty fast, greater than 3000 meters per second, because it's like you and your friends are holding hands, but they're stiff arms. And as soon as the sound, the vibration happens here, it travels very quickly through a solid. So when you're picturing sound waves being created, you can imagine like the hand would be like the tuning fork or the speaker vibrating, and it causes the air pressure waves to move across and over to your ear. So let's talk about sound. Here, this is a sound generator. It generates sound tones at different frequencies. Here's 450 hertz. It sounds like this. Okay, and then you can change that. Maybe go to a higher pitch, maybe at 1050. This will be more of a high frequency sound. All right, we can go to even a more low frequency sound. Sounds like this. So a question I have for you is, what is the wavelength of this sound? Think about that for a moment. 250 hertz sound. What's the wavelength? So it's almost like a word problem. What's the approximate wavelength of a 250 hertz sound through air? Well, you know the frequency, 250 hertz. Another piece of information we know is the approximate speed of sound in air. It is about 350 meters per second. So we know the speed, 350 meters per second. So we can use the wave equation. Remember that? The wave equation? Speed equals frequency times wavelength. And you just plug in our numbers. Okay, so we just plug in speed is 350 equals frequency 250 times the wavelength. And that's what we want to solve for. So I have to get rid of 250 up here and divide both sides by 250. This cancels. So I get wavelength equals 350 divided by 250, which is 1.4 meters. So the wavelength of sound of a 250 hertz sound through the air would be 1.4 meters. And instead of saying through air, if we said the problem was traveling through water. So now we essentially have the same problem. The one difference being, instead of speed of sound in air, we're going to use the speed of sound in water. So instead of 350, you're going to put 1500 right here, meters per second. And then we rewrite our equation. Speed, 1500, equals frequency, 250, times the wavelength. And to solve this, I want to get rid of 250, so I have to divide both sides by 250. And then this cancels. And I end up with 1500 divided by 250 is 6 meters. 6 meters. So that's about 4 times the wavelength as it was in air. So just by changing the medium, even though it's the same frequency up and down, the wavelength here, we could fit one wave in the same amount of time that we would fit 4 waves if it was in air. 1.4 meters, 6 meters. Well, what if there's lightning? Lightning. Oh, remember lightning comes with thunder. Little demonstration here. The thing is, you can see the lightning almost right away. The speed of light is really fast. It's almost instantaneous. Not quite, but almost. You sense the lightning right away when you see it. But then it takes a while for the sound to travel to you. Let's see if we can figure out how far away this hypothetical lightning strike is. If I hit play, as soon as I see the lightning, I can time it and then stop timing when I hear the sound. Let me move these closer together so I can push this better. Alright, here we go. So play, start. That was the lightning. I'm waiting, and that was the sound. 3.24. So let's think about that. Here's the time it took, and then we also have speed. The speed of sound in air, 350 meters per second. So what I got is time equals 3.24 seconds, and speed equals 350 meters per second. Our good old velocity equation. Speed equals the distance over the time. And we just rewrite those things in there and solve. So I get 350 equals the distance, which is unknown, divided by the time, 3.24 seconds. So if I multiply both sides by 3.24, multiply both sides by 3.24, then that'll cancel there, and we end up with the distance is 3.24 times 350, which gives me 1134 meters. So in that little simulation, basically simulating a lightning strike that happened 1134 meters away, or that's 1.1 kilometers away. So you can do the same thing for any kind of problem like this. Anytime you can observe something happening and then sense it or hear it later, you can use the speed of sound to figure out how far it is. Let's try this one. For example, you're watching a basketball player practicing outdoor courts at school. You know, he's bouncing the ball there out in the courts, and you notice that you see the ball strike the ground, and then you hear it bounce 1.2 seconds later. So the question is, how far away is the basketball player from you? So remember, we've got our speed of sound in air, 350 meters per second. So once again, we're looking at the time 1.2 seconds. The velocity is 350 meters per second. Okay, and we have our equation. Speed equals distance over time, and then I can rewrite that with our variables in there. Speed 350 equals distance over 1.2 seconds. All right, we gotta get rid of the 1.2 seconds. We're dividing by 1.2. The opposite of divide by 1.2 is multiply by 1.2. So multiply both sides by 1.2 seconds to make sure that stays equal. So the bottom there cancels that. So we get the distance is 350 times 1. And we get 384 meters. So that's how far the basketball player is from our ear, based on the speed of sound through air.